Why, hello there, lovely ones. So we're busy going through Chapter 9 of my action series, the consolidation exercise, and of course it's about geometry, more specifically circle geometry. The first thing to always do when you have a geometry question is to list all of the things you can see and you can't see. Yes, this information is important, so let's read through it first. In the following sketch, CF is a tangent to the circle BCD, and C1 is equals to x. So the circle BCD is this one over here, and let's be fancy and let's try paint it in. So we're going to paint in that circle just to make it easier for us to see. Looks pretty, doesn't it? And that last little bit, there we go. Okay, so that is circle BCD. And if I want to do the tangent, sorry about all of the going all over the place, I'm going to highlight that over there. Okay, so let's look at the list I made of things that I see and I don't see. It's really important, this what I don't see, that you think about it carefully and you make sure you list everything, because that helps us to cross off things as we go. So the things I don't see is over here in either one of the circles. I don't have a cyclic quad, and that means I'm not looking at the exterior angles of cyclic quads. I'm also not able to find the opposite interior angles of a cyclic quad, that they are supplementary. Then another thing I don't see is a diameter. I see radii of this pink circle, but no diameter that goes through the small circle or the big circle. And that's important because if I don't have a diameter, it means that I can't do angles in a semicircle. So no right angles from that. And then one of the other things I can't see is that I don't have a radius that's perpendicular to a chord anywhere. And of course that means that I can't prove that there's any right angles happening or that a chord is being bisected. Things that I do see. I see that I do have the tangent CF, it's going over there. And if I have the tangent CF, it means I've got tan chord theorem. And let's make this more obvious by highlighting it. So if that's the tangent, I hope you can see this, where x, so that's C1, and according to all of this, B1, let's highlight that. B1, that beautiful triangle, this particular thing, B1 is going to have the same value as C1. Also, in the bigger scheme of things, there's another triangle that's happening, and let's make it green. And in that triangle with the tan chord theorem, I know that C4, C3, C2, and C1 are going to have the same value as B1 and 2. And whether that's useful or not at this stage, we don't know. Other information I'm given, and this is really important to note, is I have parallel lines, and they are BD and CF. And looking at those particular things, I can see, and let's make it more obvious, there's a parallel line, and there's a parallel line. So I can start seeing things like alternate angles, even over there, there's alternate, and over there. And even this one, and all of those can all be co-interior as well. So let's actually just fill that in. We've got co-interior angles, and I'm not going to fill in all of the other information. We don't have any corresponding angles that I can see right now. Actually, wait, we do. We have a corresponding angle over there and over there. So yes, lots happening. Let's write down corresponding angles, and we do a little thing. Another thing I see is I've got a center of a circle, and if I've got a center, it means I'm going to look for radiuses or radii. And I do see that I've got two radii. There's OC and there is OD, which means they're equal, and that also gives us an isosceles triangle. And I know by now it's looking really, really ugly. Don't worry, we are going to clean it up. So there's our isosceles triangle, and funny enough, it's called OCD. With angle at the center, we can also look at angles at the circumference. So we have, it's really getting beautiful. We have that angle at the center and we have that angle at the circumference. See how they both come from the same chord, that point and that point, which means that O is twice as big as B1. So that is twice as big as this over here. And lastly, I saw that I did have a chord, which means I am looking at angles in the same segment, which of course means there's our angles in the same segment. D1, let's color in more. D1, not that we can see it anymore. D1 and A, where's A gone? So it's that over there, and this happening over here. These two are equal to each other, and of course those two are equal to each other because angles in the same segment. Now, using all of that information, we're going to answer these questions over here. Just to warn you, question I does have a typo. They were expecting you to find the angle O, and it's a funny story, but I'll tell you just now. So here is the cleaned up version, and we're going to use that to name with reasons 3 other angles equals to x. There is a massive lines over here, or there are a massive lines over here. And one of the tricks with working with geometry is being able to get rid of some of those lines in your head. But sometimes it helps to just see them with literally scribbling over stuff, which is exactly what I've done over here. Remember I said that we had parallel lines. And so what I've done is I've scribbled over all of the other stuff so that I'm just looking at the parallel lines. And remember I said they were alternate angles. So if this value over here, angle C, is x, it means that D1 is also going to be x. And the reason is alternate angles. What's very important with this is you must say which lines are parallel to which. Otherwise, you're just telling me positions. You're not actually justifying why they're equal to each other. So after I did that, I looked at the image again and I scribbled out some more stuff. So now I've got rid of all of those interior lines and I've just got the exterior angle of the triangle that's happening there. It's not the complete exterior angle, but it is tan chord theorem, which says that the angle over here between the tangent and the triangle has the same value as the angle on the other side. I know this can be confusing to look at, so let's just scribble that in quickly. Maybe I use a thicker thing rather than you listening to me scribble. Okay, there is my triangle, well, the one side of the triangle, and here is the other side. And I've chosen green and blue so that I can emphasize the fact that they are using different lines, because sometimes it can be difficult to see which ones are opposite. But by doing this, I can see what's happening there. In terms of the reason, I'm going to say that B1, which is this over here, is equals to C1, and C1 had a value of x. And the reason it is because of tan chord theorem. It's quite important to carry on referencing the angle where the x is. And they only asked for 3, so I'm going to go down to the last one. And once again, you'll see that I've scribbled out a whole lot of things. I have already proved that, and let's just do it in red. I have already proved that D1 is equals to x. So I'm going to put that there just to make it more obvious, which means that A is also equals to x. And the reason for that is they are angles from the same chord, or we call angles in the same segment. I suppose that's terrible grammar, so let's just, there we go, in. And now it's in red, which will drive me crazy. So there we go, we've got the 3 angles that are actually equal to x. Now you'll remember a little earlier I said that there was a typo over here, and I said there was a funny story. Funny story is I spent so long trying to figure out, the original question said, what E is, and I just couldn't connect the dots to get there. So then I cheated a little and I looked at the teacher's guide and I saw that they were just asking for O. So that seems to be the typo that's happening there. The question is much easier now because we are looking at angle at the center. Remember in the beginning we spoke about that? And of course angle at the center is 2 times the angle at the circumference, and let's do some highlighting just to make it obvious what's happening. The angle at the circumference is B1 and the angle at the center is O. And you'll see I've just written that down. Okay, and the last part of question G is to determine the value of D2. Now there's a lot going on in this question, so let's just try and erase all of that and let's focus on the triangles that are happening. Once again, you'll see that I have written things in different colors. Let's get my highlighter out. Just follow my thought process. I've got triangle OCD, and I've done that in red. Then I'm going to talk about the tangent over here, so let's do that in blue over there. And I'm also going to talk about the isosceles triangle that's happening over there, and I do that in green. Once I've done all of that, we then get to the final proof. So, in triangle OCD, I'm going to prove that it is an isosceles triangle, and the way I do that is showing that the radii are equal. The reason I want to do that is I want to show that these base angles over there we go, and this one over here are equal to each other. So now that I've done that, I can move on to my next thought, which is about the tangent. Oh, I didn't write a reason over here. So it's going to be tangent is perpendicular to a radii, or radius in this case. So there's the radius, there's the tangent. This over here is equals to 90 degrees. Try and make it seeable. And that helps me because now I can say that OCD, which is, oh my word, this is getting messy, but OCD, which is that over there, is going to have the value of 90 degrees minus x, and that x is that part over there. Now, if that has a value of 90 degrees minus x, it means the other base angle of this isosceles triangle, ODC, is also going to be 90 degrees minus x. I've already said they're equal, so I don't need to state again why they're equal. Now my next train of thought is that angle ODC, oh my word, let's get rid of some of those, ODC, and we'll go over it in green, there we go, that over there is the same as D1, which is over there, added, well, D1 is the blue, added D2. In the previous question, we proved that D1 was equals to x. So now we're going to take that information. We say that ODC is equals to D1 plus D2. We know already that ODC is 90 minus x, and we know that D1 is x, and we rearrange it so that D2 is the subject of the formula, and we come to a point where D2 is equals to negative, well, 90 minus 2x. With that, it's enough from me. Much love.